I'm just pulling things back up. Gotta log in. Launch. There we go. So let's just pull up schedule. Here we go. Calendar. Due dates. So goal is submitting project 1 today. How's it going so far? Let's see where my camera's pointing.
How do they measure the temperature of a corpse?
Of a corpse? I mean, you can do like IR, like just boop. I mean, I guess you could put a thermometer in, right? But that actually is kind of standard practice of like trying to estimate time of death. And I'm pretty sure they would just use like an IR, like a non-contact temperature measurement. As the crime scene? Yeah, so you can use like a non-contact like IR measurement. Yeah, logistically, you do need the data somehow. And really all, like to get time of death, like you're just looking for trend. So even if your thermometer is off by a degree, if you know like the rate of change, you can back calculate like when was it back at the original temperature. How about Euler method? Is that one? Euler method, and then like the idea of converging. Those are like brand new. There's no reason that would have come up in most classes. Most of the time when someone says like solve this problem, there's no issue of like, did my answer converge to the right answer? Because it's just x equals 2, and that's just the answer. But numerical methods is kind of cool because you have this idea that you don't have to do all the math, but you can just keep getting a better approximation. So as long as you can show that it converged to an answer, you're pretty sure that it's the right answer. Nothing right off the bat. Okay, let me check in, see what else comes up. What did you do for Euler to show convergence? Okay. All right, so just had a nice conversation about like Euler integration. So I just wanted to share. I like. There we go. So we have like an equation in the Euler method. What we're doing is approximating derivatives as steps in temperature, steps in time. So rather than saying like this differential equation is true, I'm saying this like difference equation is close enough. And if this is the case, if I can say that a change in temperature over change in time is that value, then delta T is negative K T minus TA times delta T. So the amount that my temperature will increase over a short amount of time is K times that difference in current temperature minus ambient. And kind of makes sense, right? Like we haven't done anything. All we did was like forget all of the first like 3 weeks of calculus and plug it into an algebra equation rather than calculus. So now, if I say like, here's T time, temp, my initial temperature is 85, then the next temperature is that, I'll call it like 1/3 T minus 65. So 85 minus 65 is 20. So negative 20 over 3 times however big my time step is. So the bigger the time step, the more I'm going to I'll drop down like that, kind of like that, kind of visually thinking about like what is this Euler method. And because we said like derivatives work when dt goes to 0, we can't get it to 0. We can't multiply stuff by 0 and actually go forward. But the smaller our time steps get, the closer it should become to the actual function that we're trying to do. And there's different ways of showing that we're converging to that function. So I was as I was walking around, I wanted to see like how people are trying to do it, thinking about it. How's that? Make sense? No sense. This is all witchcraft. Let's see. I think I started doing So I started to show like what happens as we keep making time steps smaller, or increase the number of time steps, kind of 6 of one, half dozen the other. If you're going 0 to 3 and you take 20 steps, that's smaller than taking 5 steps. And my dt keeps changing. So one way to show that it is converging is like just visually look, things are going towards the line that I want it to. And if I show like the actual analytical, so I call it and that's how I kind of differentiate, am I using a numerical method or did I solve it by hand? Analytical things are like, you solve it, there's an actual function, you can evaluate the function at any point. It doesn't matter how many time steps I have, it's always going to be the same black line. Versus numerical, like converge to some kind of result as dt gets smaller. So we could label these, right? was wrong there? Oh, I need a colon. So now I can see blue, big time step, green, small time step, green and black, no real difference, at least not that I can see. But maybe as you kind of look at this, we can see really the error is coming up right at, like, the more time goes on, the more error we're kind of adding to it. So what we could do is just compare the last value of temperature and look at like an actual convergence of like how big of an error did I introduce because I took large time steps rather than small. Let's see. And here it's negative, these errors, so let's make absolute value. Now we can kind of see like smaller time step, smaller error, and then with a plot like this, we're actually looking at error, like what is the difference between value that I think it should be and the actual value that I calculated. Now we could go like deeper, right? We could get 1001, 2001. And then start looking at a log plot of like, and this is what I expect for Euler method, that if we're approximating differential equations with straight lines, the small, like if time step is 10 times smaller, error should be 10 times smaller, like a 1-to-1 approximation. And the nice part about looking at like a plot like this is it's a little cleaner. Like you're not looking at 7 or 8 different lines trying to figure out which one's closest. But they're both kind of showing convergence, right? Is it converging? All right, so there was, wait, why is that? There's the question of like, how do I actually solve for when temperature was 98.6? How have people done it so far? Is this done already? What was your, yeah?
I just like set it to have a time that was like where the temperature was 98.6, and then I used the log to like integrate your derivative formula. You can get back to like normal formula, so you would get like the time that it died is the natural log of the live temperature minus the ambient temperature divided by the temperature at minus
Yeah.
the ambient temperature divided by negative K, and then you get a negative time, but then you just, okay, like from 11, you go back down.
Yeah, okay. So using like this formula, right? Like saying here, if I plug in a 98.6 over here, my T0 is 85, then solve for time. So natural, like take the ratios, do a natural log. What if I was like, no, I don't trust that equation. I want to use my numerical methods. Like I want to use Euler integration to solve for it. How would we do that? Like, can we do the same thing of like plug in a number and solve for when it was 98.6? Or solve for the time when we had that? It's different, right? Because all we have is just like a whole bunch of numbers. Just like, here's the temperatures for the last 3 hours. It's like, okay, well, I don't have, so then I have to calculate temperatures before 11 a.m. So one thing what we could do is, let's grab this stuff, bring it down here. Yeah, let's go 0 to 2. But instead of subtracting, I'm going to make it negative time steps. So I'm still going to start at time 0, but I'm going to work my way backwards until I hit 98.6. So it's reversing that exponential decay to an exponential growth, which makes it like if you go backwards, it should look the reverse. So now we're looking at it the reverse of, like, as I go along the right, I'm going backwards in time. Temperature was rising. At some point it was 98.6, maybe like 1.25 hours ago, according to this plot. But how do I find like that number, where that happened? Could I say when is T 98.6? It'll give me a whole bunch of falses. And if I look at the number of true, if you sum the number of trues and falses, then you get the number of trues. It was never 98.6. Why not? How come? I mean, it looks like at some point it had to be 98.6, but how come it's not saying that it ever was 98?
Are you graphing finite points, and none of those finite points are exactly 98.6?
Yeah.
Give some range.
Yeah, so probably there's like a 98.597 or something, like something really close, but it's not going to be exactly equal. So there is, rather than like an equal sign, we could do np dot is close, and it still gives us like a true false kind of thing. Let's say, and I always have to look up how to use functions, even when I've used them like 100 times. Atol, so let's go atol. Let's say if we're within 1/10 of a degree, so these are all the times that I was within 1/10 of a degree. And look at that, 98.59185. I'd say that one's pretty darn close. So we could even go less. So is close is a nice way. That's one way of kind of using, finding numerical methods that way. And since I did that, I can also say so I'm trying to look at time and temperature. So at time 1.167, 1.168, I was within 0.001 degrees of what I was trying to get to. So it gives me like a nice range that way. So that's a good way to do it. And if I want a more accurate result, I need more time steps. And you can get there even a little closer. We'll look at other ways of defining this, but at least for now, like the quick and dirty tools is a great tool to like, it gets you as close to the answer as you want to define, and you can kind of play with what parameters you want to use for it. How's that? Then we'll look at later we'll do more like root finding methods in module 3, where we define a function and find like when is that function solved. Oh, two different problems. This one is like needles being randomly dropped on a uniform grid and seeing which one's crossing. And then that one is saying like at a square being randomly assigned points. The ratio of points in the square versus the ratio of points in the circle should be higher than 4.
When I do this one though, if I put in 2 over the answer, I get double that. As opposed to 1.
Yeah.
Working.
Yeah, wrong. But that would be probably you're only counting half of the crossings. So usually what happens is you define drop the needle, you define this side as x plus I over 2. And this one, or sorry, x was cosine, and this side is x minus cosine. It's also the case where it's 180. So it's minus from now the bigger one you didn't check for.
So every needle is
No, every needle's 1. It's just depending on the angle you set it lands at. Sometimes the right side, the thing that you consider right, that is going to be on the right side, is actually on the left side.
Because what I did is I created all my random values. I created x positive and x negative for the endings.
Yeah.
And then I used
And that's like here, cosine is not always a positive number. So when you set it to negative, you assume that it's negative, but there could also be there's a whole nother set of pairs, more than less than.
okay.
And you can sum both of them.
Will it just be exactly double though?
It should be double because we're dealing with random numbers. It's not always exactly double, but it should be double.
So do I just pick another basically set of these where I flip everything that's good?
Yeah, like right now, it keeps it here, but it's called a boundary.
Yeah.
Summing.
Stop it. That is crazy.
I was just counting the number of things.
Oh, okay.
It's really funny to hear.
Well, it should be.
It's boundary before it is not.
It should be the sum of those
Oh, because it's a where function, how it's array versus
yeah, it should output an array of true and falses.
yeah, and then the blank is giving me,
It only gives a number of truths.
it's only giving me the truths, yeah.
Oh, okay. All right. Then it's not double. I didn't realize it did that. I thought it would count the falses too.
Yeah. Guess not. I mean, it's giving me a number nearby, so.
Yeah. That's good. So you could run the same 2D and do like a plus equals at some of those cases too.
Okay.
No, I'm not.
Let's do like this.
Okay, so we got like 2 more minutes. If I go and tell the chief, hey chief, the body was found 1.17 hours before we got there, like that's the time of death. What time is that? Yeah. 9:50? You just, do you think in fractions of hours? Is that why?
No, I already did it.
You did it, yeah. So this is, it's a subtle but very, very like obvious, like keep track of your unit, like use units that people actually can use. 1.17 hours from 11 a.m. means nothing to anyone. So like you gotta take, you're all like very smart, very capable, but it's easy to get wrapped up in the problem and forget, like humans need to understand what you're saying. Like you can't, not everyone is a computer. So we gotta take a second of like, all right, 1.17, it's gotta be at least 10 a.m., right? So it's 10 a.m. minus 0.17 hours. And here 167, we'll call it like 1675, right? And I'll say like, so 49.95 minutes. I could call it 50 minutes, right? So then it would be 10 a.m. minus all that. So meaning somewhere around like 9:50. Ooh. And here, print statement would be better, but 9:50 a.m. If you're worried about the seconds, and you could do another 0.95 times 60 and figure out how many seconds, but I don't know, how close do we need to get? At least to the minute is pretty good, right? Anyway, just a quick reminder, you do need to work with humans, as frustrating as we all can be. At some point, we do need to talk to each other. Cool. Is that it? Done with project 1? Send it. Move on to module 2.